So we have a session this afternoon. I don't have my piece of paper actually on what the exact title is. On networking the disciplines. And first of all, I'd like to thank my colleague Katie Russ in economics, who actually organised this session. And from my viewpoint as an economist, this is a remarkably multidisciplinary session. And that word's used a lot. The Chancellor was using it this morning. And particularly for people in economics, they're very nervous about that, right? And you know, even publishing in PNAS, I mean, what does that count for? You know, that's not really an economics journal, right? And at the same time, some economists are reaching out. You know, Burkhard Skipper's been involved in neuroscience. This morning's talk by Brenda McCowan, one of her co-authors of one of the papers, was Oscar Jorda, who's a monetary economist in the economics department. But the main reason I'm bringing this up is that we have 3 speakers today. 2 of them are really multidisciplinary and cross-disciplinary. So one, Susan Athey, is an economist who has worked a lot with people in other disciplines. And the other, Raisa D'Souza, who I'll introduce later, is also really working across the disciplines. And, you know, and this is one of the hopes, and actually one of the interesting issues. You know, we're looking at big data, we're looking at networks. People outside the social sciences have really developed those skills. To what extent will we just bring them in-house and do it on their own, and to what extent will we reach out and actually work with people in other disciplines who are using these methods? We'll see how it goes. Okay, so first of all, I'd like to introduce our first speaker, Susan Athey, who's the Economics of Technology Professor at the Stanford Graduate School of Business. She has a PhD in economics, many research interests, including internet, auctions, econometrics, and machine learning. She has reached out. She, for a while, was chief economist at Microsoft, and for quite a while has been a consultant at Microsoft, and that's really influenced her research and interaction with others, and also influenced the people she's working with. She's won many awards, including a member of the National Academy of Sciences and the American Academy of Arts and Sciences. But in addition, economics is really, really tough on giving out awards. You know, I don't understand why. I don't see how it helps the discipline. But there is one award given by the American Economic Association, the John Bates Clark Award, which is given not every year, but every other year, to that American economist under the age of 40 who was adjudged to have made the most significant contribution to economic thought and knowledge. And Susan Athey has won that award. So we're very delighted to have her speaking. Thank you.
Thanks so much, and thanks for putting together such a wonderful conference. I was talking with Matt Jackson earlier and said, you know, one rule I think I've learned from today is you never want to go on stage after someone who has 750,000 YouTube hits. So, you know, we'll all just have to do our best. That was really fabulous. I really enjoyed your presentation. So I'm going to talk today about a different kind of network, a market network, where the interactions of the individuals are not as much social interactions, but actually competitive interactions. And so this is, in some sense, this observation that you can think about markets as networks is an old one, and there are, you know, a variety of economic studies over the years that have taken that tack. But I would say that the sort of micro economics of that, especially that part that's been sort of studying some of the modern platform markets like eBay and so on, haven't really taken that approach. And so today I'm going to be talking about bringing together some tools from economics for studying competitive behavior with networks. So I want to start out actually by talking about A/B tests and experimentation in general. And that's going to segue into the network idea. So one of the things that, for those of us who have been sort of collaborating with tech firms and doing experiments, we've observed that A/B testing, that is randomized controlled trials, so that if you're a tech firm, you call a randomized controlled trial an A/B test, has become incredibly important for business and business practice. So somebody like Google will run 10,000 or more randomized controlled trials every year. Nothing changes on a website like Amazon or Google without an A/B test. Okay? So this is actually a really important phenomenon for our society. It also is affecting governments and development organizations who are trying to also test the effects of all sorts of policy interventions. And really technology and digitization has made it possible to do that on a much larger scale. We also see that in newspapers and everybody else who's providing our information. So one of the observations, though, about how these tests are run and what they do is that they actually really miss out on a lot. So a typical A/B test at Google would test sort of two different versions of a search algorithm. And the way they would do the randomization is they'll take, say, 1% of users or 0.5% of users as they come onto Google, and they'll allocate them into a treatment group. They're actually going to be running hundreds of experiments at the same time. It's a little more complicated than that, but so you're much more likely to be in an experiment than you are in a control group. But you're going to get allocated on a user basis. And this is something that you can learn very, very quickly. Should I use a different color blue? Should I change my fonts? Should I re-rank out my results in a different way? And I can very, very quickly learn about that. In a day or so, I'm going to have a result. I'll have a significant result, and I can decide to roll out and release these new features. And it's actually really important for innovation because, say, at a company like Facebook, pretty much anybody can change the code of Facebook. An intern can change the code that produces what you see on Facebook. And so how do you allow that kind of decentralized rapid innovation? Well, you have a very objective way to evaluate the impact. And that is to put it through an A/B test, and if it looks good, then you ship that code, you release it to the wild immediately. So it's really kind of central to the way innovation happens in these large firms. But if you're going to be testing users, it's very cheap, very easy, you're not really going to have a good idea of how those tests affect the businesses that are operating on your platform. So if you're eBay, you have two sides of the market. You have users and you have sellers. If you're a search engine, you have users and you have advertisers. If you're Amazon, you'll have the users and you'll have the third-party sellers and so on. Facebook would have users and advertisers. So it's very easy to test what users like. But trying to understand advertiser responses or seller responses is a much more difficult problem. And it's these agents that I want to focus on today. So interestingly, even though it should be like sort of obvious to everyone that randomizing at the user level is not a good way to learn about advertiser or seller response, that is the standard practice at every major tech firm. So what you would typically do is you might say, okay, I'm going to do something that's going to re-rank my sellers. I'm going to make lower price sellers appear higher on eBay, something like that. I'm going to take particular types of advertisers and rank them higher beside your search results. And I'm going to experiment on users. So what's going to happen is each advertiser or each seller is only going to see about 1% of their traffic affected by the experiment, which is like background noise to them. So from the seller perspective, this experiment really didn't happen. So what we're going to learn is how the users respond. So we can say if I put low-priced sellers higher on eBay, I can see how much more the users click, how much more the users buy. So I can learn about the user effects, but I have no idea what happens to the sellers. But it's very common just to look at the metrics and say, oh, gee, I got this many more sales, without actually taking into account the fact that the sellers might later change their prices or change their behavior or even quit eBay. Okay, so with advertisers, like what might happen is that, first of all, the advertisers don't even notice the effect. Second of all, the advertisers will influence each other, even if they don't change their behavior. So if I take one advertiser and put it up high on the page, they're going to get lots of clicks, and they're going to therefore have to spend a lot of money, and if they have a budget, they might run out of money. If they run out of money, they're off the page, and that's going to lead another advertiser to go to the top position, and then they might run out of money too. So there's interaction effects, even if the advertisers don't change anything at all. But then, of course, in an economic world, they have incentives to change what they do if you change the way the market works, and so indeed they'll change that as well. And so all of those things are generally ignored. So why are they ignored? It's not that people are stupid, it's actually that it's just very hard and very expensive to do something other than this. The user experiments are really cheap. So let me kind of give a general framework for thinking about these kinds of problems, and that is to think about these marketplaces as bipartite graphs. So this is I'm going to use the word seller for sellers or advertisers, just have one term. In e-commerce marketplaces as well as online advertising, sellers are going to compete with each other to attract user attention and ultimately purchases. And so users or consumers on these platforms are going to enter queries or select products from a menu, and the platform is going to use various algorithms for ranking them. So the economic market design problem for the platform, and that's who economists often think from the platform's perspective, they're going to try to figure out what are the ways to rank sellers that get the most consumers to my marketplace, that keep the sellers happy on my marketplace, and so on. And the tools they have, or the little dials they turn, would be things like fees for listings, fees for clicks, or percentages of sales. So just to see how this might work, suppose I'm shopping for my kids on eBay, and first of all, they say, oh, Mommy, I want a How to Train Your Dragon costume. So I can look on eBay for How to Train Your Dragon costumes. Then my little one might see me searching for my middle one and say, oh, no, Mommy, you're searching for costumes. I want a Frozen costume. So I might also search for Frozen costumes. And then we might start thinking about toys and search for How You Train Your Dragon toys. So all three of these search queries are queries that could be entered by a user. And so eBay is going to show a set of sellers in response to each one. But of course, there's going to be overlap. People who sell How You Train Your Dragon costumes also sell How to Train Your Dragon toys. But then there's people who specialize in costumes and people who specialize in toys. So this is going to lead to a bipartite graph where I've got two types of guys. I've got sellers, and they're competing because they're both showing up on the same query. And so some sellers might show up on both query A and query C. Some sellers show up on query A and query B. Some might show up on B and C. Some might show up on all of them. And this is going to lead to interactions among all of them. So one thing that's really cool about this is that actually I can measure this. I can measure this directly. And actually, as the marketplace designer, I can control this. I can manipulate it. So unlike kind of social networks where we think of them as being sort of more organic, and we can manipulate them somewhat. I can put a monkey into the cage. But here I've sort of got my monkeys, but I can actually manipulate, how close friends they are, if you like. Okay, and that's a really interesting and powerful methodology. But this is one that's really been explored from this perspective in only very little way across all of the disciplines that are engaging with these tech companies. Okay. So let me tell you quickly, this is a real-world problem. I should say that this has been a focus of a number of years of consulting for me. So I'm sort of telling you stories about, partly based on my experience with that. So there's sort of three types of solutions to dealing with this problem. The first two are to continue to do your user experiments, but to try to do a better job with them. And I'll touch on those. I'll touch on the first one briefly, talk a little bit more about the second one, and then the third one is the one that it really uses the network science most deeply. So the first is to just modify your evaluation of short-term user experiments. So this is where an economist or a social scientist can come in. So just actually, by the way, if those are interested, like how do social sciences add value to the hundreds of machine learning people in a tech firm? Well, this slide is a very simple example of how one social scientist can have a very large impact very easily. So you conceptualize the problem and you attempt to address it with alternative measures. So for example, in search, an advertiser's bid is going to be responsive to what the quality of their clicks are. That is, if I'm selling auto insurance and you put my ad up when somebody searches for dental floss, then the person might click on my ad, but I'm not going to sell very much auto insurance. So that's a low-quality click. On the other hand, if they put me up on somebody searching for car insurance, that might lead to a high-quality click. And so if you ignore advertiser behavior, then you're going to be very tempted, especially if you need to make more money this quarter, like Yahoo did for a number of quarters, you might be very tempted to put auto insurance ads on dental floss queries. Because in the experiment, it's going to look like it's going to make you a lot of money because the auto insurance guy is paying $30 a click. So you get a few more clicks, that's very nice, except for later on you think they might lower their bids if you keep throwing them up against dental floss. Okay? But that will never show up in a user-level experiment because the advertiser won't actually see the change and respond to it. So one way to kind of avoid this innovating in the wrong direction is to change what you measure. So of course, if I put up auto insurance on dental floss, then somebody clicks on the ad, they're very likely just to quick right back to the dental floss query because they weren't really interested in auto insurance. So what I can do is that even though I actually made money from that click, when I count the money I made from the experiment, I'm going to throw that money away. I'm not going to count it. I'm going to say that's bad money. That is bad money in the sense that that's not sustainable money. And so when I evaluate the experiment, I'm only going to count good clicks. And this is also something that I've advised to news media organizations as well. When they start becoming data-driven, there's a temptation to put like kind of junky headlines and so on. You've all seen more and more of this, right? Like you got weird in all the newspaper headlines these days. The weird thing you found out about this, that's because people click on that, but it doesn't really make you like the New York Times in the long term. So I would throw away those clicks and not count them, even though the New York Times in the short run makes money from them. A second example of this is that advertiser spending is going to respond to the return on investment, and so you can just tell the engineers, you cannot build algorithms that for whatever reason raise prices for advertisers. You're not allowed to do it. You have to solve a constrained problem. You can try to improve your ranking algorithms, but if it raises prices, we're not going to ship that product. That's also, of course, a very limiting thing to do, but it's a way to sort of prevent yourself from harming the marketplace. Now, as you can see, these types of solutions, they can help. They're sort of a Band-Aid, but they're not really a fundamental solution. So the second thing, and this is actually really the bread and butter of economics, but almost no other science, so this is where we're kind of unique and weird, I would say, is that economists actually believe that we can build models and make predictions about counterfactual worlds that nobody has seen before. So, many people think we're quacks for doing this. In fact, people inside economics think that we're quacks for doing that as well. But it is something that we try to do, and we have at least a set of pretty well-defined and well-developed literature about how to do that as well as possible. So the kind of simple way would be to try to just have a simple model that relates short-term outcomes to long-term responses. The second is to do something more complicated we call a structural model, where we actually write down a functional form equation for what somebody's objectives are, and then assume that they follow those objectives. And so if we change their environment, if we know what their utility function is, we can predict what they'll do to maximize that utility or even solve for a new equilibrium. Okay? So just to give some examples of each of these, here's an experiment that I ran on Bing where I swapped search results. So I tried to see what would happen if you took the thing in the first position and moved it down to the third position, or moved it down to the fifth position, or moved it down to the 10th position. And so what we found in this randomized controlled experiment was that you lose about half your clicks, a little more than half your clicks, if you move from the top position to the third position. Okay? And of course, this is a very big policy issue right now as well. So this is a general effect, but you might imagine that this effect is really quite heterogeneous. So the effect of re-ranking stuff is going to matter a lot. Like if you know what you're looking for, if you type in Bank of America and you put the Bank of America link in the third position, you're just going to be annoyed and click on Bank of America in the third position. So in fact, in our experiment, we threw out those really, really clear queries because that was just viewed as unacceptable to the user. But even within queries that are not quite that clear-cut, there often is something, they can be more or less navigational, be more or less clear where you want to go. And there's other types of effects as well. So in some work with heteroimbins, we've been working on modifying machine learning methods to try to estimate heterogeneity and causal effects. So this actually requires changing machine learning methodology because that methodology is designed to predict outcomes, not to predict causal effects. And causal effects are actually, there's no ground truth. So I don't know for any of you in the audience exactly what your personal causal effect is. Therefore, traditional machine learning methods, which work on trying to predict people's outcomes using observed outcomes as a ground truth, don't work exactly right. So I won't go through all the details of that. There's the National Academy had a recent symposium, and I have a talk on that that's available there if you're interested. I'm just going to show you now applying that method to the search example. We're using a machine learning method called regression trees, except for modified to predict causal effects rather than just predict outcomes. And so what we get when we apply this method is that we get a partition of the query space into subsets, and within each subset, we estimate a causal effect. And so we're able to see, for example, if the query is classified to be a good candidate for images and also to be likely to be about celebrities, there was no effect of re-ranking, because if you were looking for a picture of a movie, if you were looking for a movie star and you saw lots of pictures of the movie star, you don't really care about the informational query, the results. But for other types of queries, there was actually a very large effect, even larger than average. For example, things that were rated to be related to Wikipedia references, more informational queries had a much larger effect. And so we can then, each row here is a subset of the sample. We can actually estimate the treatment effects in each part of the sample. And we can then use that to do a much better job predicting what's going to happen. Because we can say, well, you know, here's some branch where there's a really big effect, and then I can try to understand, well, do those types of advertisers, are they very sensitive to quality? Are they very responsive? Are they very, very active? There's more likely to be a big response by the advertisers in those parts of the space. So this is obviously it doesn't require a lot of assumptions, but it's also very limited. I can say qualitatively whether a particular change is likely to affect a particular type of advertiser and whether that's going to have an effect, but I'm not going to be able to do a very good job of putting quantitative responses on exactly how much of an effect it's going to have. So a second approach that I've used is to actually build this full structural model. So we're going to assume, in my first paper on this, we assumed that the advertisers maximize profits. It turned out that that model did a pretty lousy job predicting behavior. So we then built a much more richer model where we allowed advertisers to have one of a dozen objective functions, where some of them trying to get to the top position, some of them had budget constraints, and so we actually used the fact that we were constantly experimenting on them. Every week we're changing something about how the system works, and we have lots and lots of stimuli. And if we see the same person responding to 10 different stimuli, we can classify which type of person they are. And so we use this behavioral model, and then we have to go back and try to calculate if I made some other change that I've never made before, how do I think they would respond? And that's where we get into one of the big network computational problems. My paper actually looks at a subset of the keyword bids on the system. I've got tens of millions of bids that I'm modeling in my sample. That's a subset of all of the different keyword bids in the data set. So in principle, I would be computing an equilibrium of a game between a couple of 100 million players. That's hard. My computers can't do that very well. But if I can use something about the network structure to say that, well, really, they don't all 100 million or a couple 100 million don't care equally about the other couple 100 million, we can find communities and segments and try to compute equilibria there, and then try to reconnect them. So I'd say this area is very much open for research, how to compute large-scale equilibrium in sort of a reasonable way. So we are doing it in a very hacky way for our paper, because that's not the main point of our paper, but it's something that is very useful for these tech firms, and it's going to become more and more common for all the people studying networks to have these very, very big networks to try to worry about. Okay? So the last thing I'll talk about is network experimentation. And so in network experimentation, we're trying to think about actually running experiments on the network itself and really take advantage of running not user experiments, but seller experiments, directly experiment on them. So to do that, the sort of way that's developing in a nascent but rapidly growing literature is to think about grouping my sellers into communities. Now, I should say this has been mostly applied to like Facebook, not to my market networks. But for the user networks where it's been applied, we group the sellers into communities. In my seller context, I'm going to do it by taking a bipartite graph, weighting links between advertisers and queries, using weights in terms of how much business they do. And the big problem I have is that spillovers are large. It's not like there's like just the guys who do toys on eBay and just the guys over here who do laptops. There's a lot of people who cross over a lot of categories on eBay and on search. And then we do the experiment at the cluster level, watch them for a long time. So just to kind of see how this might work, I could run a community detection algorithm, something like, oops, is that, now my fonts are messing up. I thought they were okay. Let me see, am I going to lose? well, I'll see. I've got a PDF on here somewhere. So what the Newman et al. Algorithms are doing is they're trying to find communities where there's lots of interaction within a community and not a lot across, and these orange units are ones that have a lot of spillovers. Okay? So then I'm going to randomize at the community level and try to analyze that data. Now, I've got a bunch of problems. One is, how do I deal with the spillovers? My observations aren't actually independent, so how do I do my statistics? And also, these kinds of designs make it easy to study, like, well, what would happen if a whole community got treated or if a whole population got treated, but they make it actually very hard to study peer effects, because most people either had all their peers treated or none of their peers treated. You don't see a lot of in between. So one approach to this, proposed recently by some computer scientists, was to basically define being treated as having, say, over 60% of your neighbors treated, and then use propensity score weighting to adjust for non-random assignment to this condition. But this is really an open research area of how to do this, and this is something that I've been working on. So let me briefly tell you about the way that we've been studying testing hypotheses about peer effects in networks. So to do that, I first just need to really briefly introduce the approach we would use to studying networks if we were experiments on networks if I just had direct effects. So imagine I've got an experiment, I've got treated guys in yellow and control guys, and I'm trying to test hypotheses. So the approach that has been growing in popularity in doing this is something called randomization inference. This is how we can do the statistics. And so the way it works is I can say I'm going to have potential outcomes for each unit. Say unit A, I saw him being treated, so yi of 1 is his outcome if he was treated. But I don't know what his outcome would have been if he'd been in the control group. And that's my fundamental problem for inference. Wi is his treatment assignment. He's 1 because he was treated. So now I can say, well, how can I figure out what the effect of the treatment is? Well, first of all, I can say, what's my point estimate of the treatment effect? The average of the control guys is, I've got 2 and 4. So the sum is 6, the average is 3. In the treatment group, I've got 3 and 5, the average is 8. Oops, I flipped the sign there. And I want to see what's the p-value of, oh, no, these are, I'm sorry, I did the opposite ones. These are the real treatments. So 3, 2, 5, 4 are the real treatments, and I want to understand what the p-value is. So the treatment effect is -2. So the randomization inference approach says, well, under the null hypothesis, there's no effect of anything. I actually know what your outcome would have been if you hadn't gotten the treatment, or I know what your outcome would have been if you had been in the control group. So I fill in under the null that your outcome would have been the same under either of those. And that's what's called a sharp null hypothesis. A sharp null hypothesis is one where you know exactly what would have happened in the alternative treatment regime without under the null hypothesis. And so then what I can do is I can say, well, I can imagine under the null, it doesn't matter what the treatment assignments were. So I can think about all sorts, redrawing in lots of different ways what the treatment vectors are. Each of those, if it was equal probability of treatment and control, would have equal probability. And in each case, I can figure out what the test statistic would have been if that had been the treatment assignment. So I know that these 2 guys were treated and these were control. If I relabeled them, then I would get a different test statistic. But of course, if there's no effect, then that test statistic would be just another estimate of what this test statistic is under the null. I've got a full distribution, so I can say, the test statistic is less than -2 a third of the time, it's greater than 2 a third of the time, and that's going to give me actually going to give me a statistical significance level that doesn't depend on large samples, it doesn't depend on anything really. And so it's quite general. So this approach is going to be really good for working on networks where we don't want to make a lot of assumptions. But the problem is that, a lot of the hypotheses we might want to test in networks aren't sharp. So if I want to say, I want to test whether there's peer effects, the problem is if a treatment has an effect on me, then I don't know what my outcome would have been if I hadn't been treated. So these are what we call non-sharp null hypotheses. And so in our recent paper, what we do is we try to actually figure out how to do those types of things. So I'm running out of time. I'm just going to give you one example that shows you how we can turn a non-sharp hypothesis into a sharp hypothesis and actually use this Fisher randomization inference approach for very complex hypotheses, which allows us to then do correct tests of very interesting experiments and networks. So here's my little network. And what I'm going to start by doing is picking two focal units, A and B. This guy's treated, this guy's controlled, the red ones are focal. And I want to test the hypothesis that friends of friends don't have any impact, that only your friends have an impact. So in order to test that hypothesis, I'm going to first take my focal units and take all of their direct friends, and I'm going to call those buffer units. Okay? The buffer units are going to be their friends, and then the auxiliary units are going to be their friends of friends. And so under my null hypothesis that friends of friends don't matter, changes to the treatment status of the auxiliary units should not affect the outcomes of my focal units. And so what I'm going to do is I'm going to take, instead of thinking of that I've got all this data from a big network, I'm going to pretend that I only ran an experiment on those guys. And I didn't touch their friends when I ran my experiment. And I'm going to pretend that I only randomized their friends of friends. And then I'm going to use that as the variation that I analyze in my experiment. So I can do that, and I can look at the probability of all of the different friends of friends assignments only randomizing the auxiliary units. I can come up with the test statistic, and then I can come up with the distribution of what the test statistic should be under the null, and then have a valid hypothesis test for whether friends of friends matter. And this turns out to be a very, very general approach. It can work for lots and lots of hypotheses, and you need a very big network to get good statistical power. So we're trying to push this forward in terms of testing much more interesting hypotheses on things like Facebook and so on in network experiments. Okay, so let me stop there. Thank you.